Morning, folks. Well, for me, it's morning, so I keep saying. I wanted to say hello, folks, and leave it just a daily open greeting, but I keep thinking about the morning because for some reason I get up in the morning. I don't know why. It's a bad habit. It works every day that way, it seems. Anyway, how you doing? This is my third video now that I'm actually going to probably put on the air. The other ones I start to rant about things that bother me, and I'm pretty sure no one out there really wants to know what bothers an old man. This old man gets bothered by things like global warming, trees disappearing, and, the natural stuff that seems to irritate a lot of people. So we're not going to talk about those things. I'll try to avoid my differences on that kind of thing, right? I will say this, though. Greta, you'll know who I'm talking about. She might be a real famous girl one day. She might be a world famous girl. Anyway, good job, Greta. Keep it up. I love you. You're a good kid. So, now that's all done and said, folks, I'm going to explain eventually in whole detail why global warming is so dangerous. But I'm not going to preach about global warming in and of itself. I'm just going to explain why it's dangerous. It's a lot more dangerous than we're giving it credit. And people are going to, it's going to be one of those things where you inform people and they ignore you. And then when it happens, I'm sorry, but it's too late. That's usually how we are. We just are. Mm-hmm. So, now that that's done, I said I'm going to try to keep that light back there out of your eyes. Hold on a second. I'm going to get a drink of my coffee out of my cup. Here, you want to see my cup? There's my cup. It's a really big one, too. Okay, hold on. I tell you what. Look somewhere else. Good stuff, huh? Yeah. Cuckoo for cocoa coffee. Okay, so anyhow, on my first two videos, I introduced, the first one, of course, I'm introducing the whole process of me making videos and going on the internet. I did, in fact, get a headset, and I also got, I don't know if it's Bluetooth or not, but it's wireless. So then I downloaded the Slobs program so that I can show folks what it is I'm actually talking about when I'm looking at Google Earth and things of, not everything that I talk about is on Google Earth. So I get a lot of material from the, I'm trying to think of the name of that place. What is the name of that place? It's like, we have NASA, and then there's, the European one. European Space Union, those guys, or something. European Union Space thingy. Anyway, I get a lot of things from them. Well, not a lot. I get pictures, but they're very helpful. Compilations is mostly what they are. And, the Solar Dynamics Observatory is what I'm going to use to describe how there are similarities between gas giants, terrestrial planets, and, of course, stars. Yeah. I had to think about that for a minute. It's like, what was the other one? Oh, the sun, of course, solar dynamics, right. Yeah, that's right. Okay, put the two of them together. Okay, so now it's a funny thing because I finally figured out how to go in there and to YouTube and come up with a thumbnail to replace my terrible facial expression of my 3 terrible facial expression photos that it offered me. And it's a thumbnail that shows the title of the story of Earth. And then I go into very detailed information on basic structural, I don't know of a good word to call it. It's just the way the planet works. And it doesn't really mean, there's going to be a lot of folks out there that just aren't going to buy into this. I've already spoken to a couple of scientists, one in person, one through email, and, 2 through email, and pretty much get the same treatment every time because plate tectonics is considered to be the only possibility. And I'm going to very clearly explain why it's not. And there's kind of a sore spot there, credentials. Well, well, that's like, well, okay, credentials. Huh? No, I'm sorry, I don't have any credentials. Well, last time I checked anyway. Oh, hold on. Actually, let me look at my cough right now. It might be in my pocket right here. Oh, it's not that pocket. Oh, I don't know where I put those credentials. Oh, you know what? I tell you what. I'm gonna go down to Walmart and go buy a box of credentials. How's that sound? Will that work? I don't know. But basically, the point is, you don't have to have credentials to have a mind. Go figure, right? And you don't have to have credentials to have an imagination. All right. So now that we've established that, you know, Copernicus didn't have credentials, right? Well, I don't think he did. We seem to think that a lot of what he said is very important. Him and a couple of other guys out there, right? One of them even got jailed in his house for being smart. You know, smarter than the average squirrel. Well, anyway, because we're all smart enough to realize it and understand it. We're just not smart enough to be open-minded enough to it, to understand it and agree with it. So basically, I'm trying to say that nothing in the cosmos is singular. It's a very large plural. It's plurality in and out all the way around. Universes everywhere, okay? Galaxies everywhere. How much further should I go? Okay, anyway, on my thumbnail, I'm going to go ahead and explain it because I actually went back and reviewed my stuff, and it's like the thumbnail isn't really addressed in either one of my first two videos. So in my thumbnail, I'm basically talking about how the planet works. And I'm going to go ahead and flip my phone so it's looking at my computer screen, and hopefully I don't wiggle the phone too much, right? Because that's one of the drawbacks to how we're doing this stuff. I don't even see the wiggity dig up here. Well, maybe I can't do it while on a videotape or recording. Oh, that stinks. Oh. All right. Well, if you happen to have the opportunity, go back and look at the thumbnail. I'm going to cover that information later on anyway. So basically, you have a commonality between all the flying basketballs in outer space that look like planets and stars. And they all seem to have this spherical shape to them, right? So isn't that something in common? So why wouldn't we categorize all of the spherical objects into one genre, if you want to call it that, and then go from there? That makes sense. Now, what works for one spherical object flying through outer space would seem to work with just about all of them. Why wouldn't it work? Physics is repetitive. So we're thinking about how physics would affect these different planets. And I'm going to tell you that planets, stars, gas giants, TSOs, terrestrial stellar objects, which I'm using and developed the term to classify black holes and white holes into one classification. It's basically just a very huge planet, and rather than having water for oceans, and rather than having methane oceans, it's going to have plasma for oceans. You know, it's pulling those stars down. Well, it's a huge planet, so it's got a lot of gravity, more than those stars can muster up, and the stars get sucked into it, onto its surface, and where does the plasma go? It floats around, into plasma rivers and maybe even oceans. Definitely oceans if you have a white hole. And oops, sorry folks, didn't mean to blind you there. And what that comes to is that black holes are pretty much always black holes. And the way that they work is their luminosity is dependent on the stellar feed, the rate of stellar feed as it is. So the more stars you have floating around a black hole, the brighter the black hole is going to be. But the black hole is always going to appear to be a black hole. Why? Because it will always have a lower luminosity than the stellar mass floating around it. So our galaxy isn't a very bright central stellar mass floating around our black holes, which we have 3 of. And so you've got, I'll explain why we have 3 later. You've basically got all this material floating around them, this stellar material. And then if you think about white holes, we don't really see a whole lot of those, and probably wouldn't, because there would be a stellar cloud so thick. It would be like looking at the Sunday paper back in the day, you know, and the comic strips where they have little teeny weeny dots that all come together, and when they do, they make a picture. And in your mind, you see a solid face versus a bunch of little colored dots making up that solid face. That's what the stellar cloud looks like around these white holes. But then the stellar cloud is so much brighter than the white hole that the white hole appears to be a black hole, no matter how you look at it. Same thing with our black holes. They're black because they have a lower luminosity than their surrounding material, or their subjects, their stellar subjects, as I like to call them. And they're like sunspots on the sun. If you remove all of the coronal mass around the sunspots, then the sunspots would appear to be extraordinarily bright and not black. But because they are of a lower luminosity, they appear black when they fall in the middle of the brighter stellar plasma, right? Makes sense. It's terrible. It's funny how these things seem to make sense all the time. So anyway, yeah, Boomy and we're gonna go ahead and explain to everybody how all this stuff makes sense. It's incredible. So there you go. Now, if we look at the top of this, I know I'm not really showing folks what the top of this. Okay, hold on. I'm gonna get a drink. Hey, I'm back. All right. Okay, so there was my coffee there. I don't know if you really want to watch me sipping on my coffee mug. I mean, it says, be a nice human. That's good. Okay, anyway. At the top of my sheet in the top right, I have a great big yellow arrow, and my great big yellow arrow is pointing to the top of our planet. And I say it's the top of our planet because it really is. It's not just the North Pole. It is actually the top of the planet. All bodies in the cosmos have a base and they have a top. I'll explain that to you later. But the force is greater at the base, just like it is on Earth. And it's weaker at the top. That's why, that's why you get great big whirlpools at the top of the planets and tiny little whirlpools at the bottom of the planets. It's spun up tighter, that's all. And I'll explain that to you later. Well, actually, I might even be explaining that to you right now. So the core vortex direction of rotation is what I'm pointing at the top of the planet. And the core vortex is the one that goes through the axial tilt of the planet. It is the core of the planet, literally. And then when you take in all of the different levels of Earth, when we break it down, and we have the crustal layer, we have the lithosphere, we have the asthenosphere to the mantle, and then we go to the core of the planet. Well, by the time you break all that down, the core of the planet is actually rotating in the correct direction, which is the opposite direction of the planet rotation, which is considered to be prograde. Prograde because our planet is rotating in the exact same rotational direction as the sun. But the core of the planet isn't. The cores of planets never do. They're always going in the opposite direction of the planetary rotation. You'll notice that if you look very closely at Jupiter. Very closely. We have videos of Jupiter that are rotating in the opposite direction. Just look. Anyway. Now, there's more to it than just that. So you have these vortices. You have a vortex at the top of the planet, a vortex at the bottom of the planet. Basically, you have a four-dimensional kind of a vortex because we have a three-dimensional vortex that occurs on Earth that we often refer to as hurricanes. But in this case, this particular type of hurricane has the hurricane that's on top, and then it's also connected and married to a hurricane that's on the bottom. So it's the anti-hurricane at the bottom, right? So these anti being because it's opposite of the hurricane at the North Pole, or the North Pole vortex, basically. And they rotate the same direction. They're both rotating in the opposite direction of the planetary rotation. So that names one vortical rod, as I refer to them, because it's kind of like a rod that goes through the planet's core. That's not the only rod. There are two other rods. And all planets, like Earth, which are differential, are gyroscopic. Okay, so in that gyroscopic property, we have 3 vortical rods. And in this thumbnail, I'm showing exactly how 2 of our vortical rods are seen. Actually, all 3 vortical rods, because I have it showing the vortical rod that appears at the North Pole, the vortical rod appearing, the vortex that appears at the North Pole, which is connected to the vortex that appears at the South Pole, making one vortical rod that lines up with the core of the planet and its axial tilt. And then the other 2 vortical rods, 2 vortices of which are visible, the other 2 are not because they're on the other side of the planet. And so we have the we have the Pacific Ocean vortex to the left on this thumbnail, and we have the Sapaliwini vortex to the right of the screen on the planet view. And the Sapaliwini vortex is actually, it has a center that is in the Sapaliwini forest of South America. That's why I named it Sapaliwini. I couldn't find anything smaller than that. It was like this great big massive forest out there, and you're like, there's not a town or a rock or something that somebody named? Well, of course there is. We just don't know what it is, and we didn't bother to put it on Google. Google Earth. Yeah. Okay, so these vortical rods, 2 vortices of these vortical rods are above the Earth's equator, and the other 2 are below the Earth's equator, and that's how they roll, literally. One end of one rod is above, while the other end of one rod is below. I'll go into details on how that operation works together to function in the way that it does. And so it's kind of like having rotary blades installed within the center of your planet. I'm going to get a drink of my coffee. Don't look. It's 3:09, and I'm going to get ready for work here in a moment. Oh, wait. I already did get ready for work. I just have to go to work. Work. Who wants to work? Oh, well, anyway. Okay, so now toward the center of this, I have the exterior vortex direction of rotation. So the exterior vortex is actually the rotation of the planet, which is a vortex. So you have the core vortex of the planet that lies within the center of the exterior vortex of the planet. Then you have the 2 other vortical rods that make up the equatorial vortices. So you have 4 equatorial vortices. So in all, you have 8 vortices and 3 vortical rods making up the 6 primary vortices. Okay, the exterior vortex is driven by solar wind pressure from the sun, and the rest of them are all driven, the core is likely driven by the backflow, if you will, from the exterior vortex that's driven by the sun. So basically the core vortex in its opposite rotational direction is driven by the exterior vortex, believe it or not. Okay, now that we have that figured out, we also know that, I'll explain to you that the equatorial vortices are anticyclonic. So that means that they're basically sucking everything in from the top down to the core of the planet. And then it gets cycled back up and down and out of the polar vortices. So your polar vortices are cyclonic because they're sucking it from the base of the vortex up through the top of the vortex. If you consider these different vortices on the surface of the planet behaving like hurricanes on the surface of our Earth as they fly around. Anticyclones suck things in from the top of the atmosphere and poop them out on the ground. And then cyclones, did I say anticyclones? I meant anticyclones. And then cyclones suck the material up from the ground and spit it out at the top of the vortical hurricane point, which then turns around, cycles the fish, and drops them on people's cars or whatever else happens to fall. I think one time we had whales fall. That might be a fetch too far, right? There was a scientist that said I was fetching too far once. That's when I said that Antarctica was connected to the San Andreas Fault. I don't mean the continent Antarctica is connected to the San Andreas Fault. I'm saying that something that I'm going to explain later in much greater detail is what I refer to as spiral density fractures. So there's a spiral density fracture that extends from Antarctica. Why? Because Antarctica is rotating in the opposite direction as the rest of the planet, because it lies on the base of the planet at the planet's core, which is rotating in an opposite direction. Come on now, look at it. It looks like a backward hurricane because it ain't going the way the planet's going, right? All right. Well, it has a whole bunch of spiral density fractures that extend away from it. The same spiral density fractures you see in your mother's bread mix or whatever mix she has in that blender bowl as the two blender feet are beating whatever's out of that whatever's in the bowl, and you see all these little spiral circly things going out, spiraling out away from the centers of those beaters, or whatever the heck they're called, petals, maybe they're called petals, all the way out to the outside of the bowl. Those are the same thing we see on Earth. I'm calling them spiral density fractures, because when we look at our galaxy and we see all the blue stars collected along these particular zones, we refer to those zones as spiral density waves. Well, on Earth you have spiral density fractures, and you also have spiral density arms. Antarctica has both. You can see this type of information up there on the North Pole. You just have to look real hard because oceanic sediment kind of covers up a lot of it. But when you look at the Earth's surface, you can see how that operates. And if you go to the top of the planet and you trace the very apparent I'm not sure how to refer to it, but you can see how weather patterns affect the surface of the Earth in terms of vegetation and agriculture. And so you see like green and brown stripes spiraling down the Earth. And the opposite direction of spiral operation than the direction the planet is rotating in. And it's like looking at especially if you look at Africa, it's like looking at a barber's thingy that spins around with stripes on it like a candy cane. And that is basically what we can refer to as the coefficient of the coefficient of solar wind pressure drag. And it's the coefficient of solar wind pressure drag that forces the continents to migrate in a downward spiral that is a downward spiral in the opposite direction of the planet's primary rotational direction, prograde. So they're actually going retrograde. It's the drag. It's a big drag. Yeah. It's more fun to look at the other stuff that's moving faster. But hold on, I'm going to get a drink of coffee. All right. Now, each one of these vortices that's at the equator on Earth and on the Sun, not so on Jupiter. Jupiter is kind of a weird animal of its own kind, but it has the similar properties of the same nature. They just don't function quite the same is all. And that has to do with something else I'll explain later. Okay, so flowing tangents you get when you have the tangents of two vortices at their perimeters that are actually flowing in opposite directions, but because they're flowing in opposite directions, they're flowing in what would appear to be the same direction at their tangents. Tangent is where the perimeters meet and touch each other. And the Earth's vortical tangents are at 45 degrees from their core. And at these 45-degree tangents is when you have flowing tangents. And then when you have vortices that are rotating in the same direction, their tangents become turbulent, because at their tangents, they're going in opposite directions, even though the vortices themselves are rotating in the same direction. When I say rotating in the same direction, I'm saying if you get two vortices that are both rotating clockwise as you are observing them, their tangents as they meet are turbulent because their tangents are going in opposite directions. Then you have those that are flowing clockwise and one that's flowing counterclockwise, whereby their tangents are flowing tangents because they meet and go together in generally the same direction. Got it? All right. And then I identify the two safest places on Earth if the Earth ever goes back into one of its states of worldwide liquefaction, where these vortices come to life and start rotating very quickly. And when I say very quickly, I mean very quickly in geological terms, not so fast like Mom's blender. Okay, if that happens, we're in trouble. We might not be in such great trouble if they are geologically rotating very fast. Okay, now I mentioned basically the cyclonic properties of the polar vortices and the anticyclonic properties of the equatorial vortices. And if you think about boiling water in your pot, that's what you're getting. You're getting a boiling pot of a boiling ball, not a pot. The pot. There is no pot. There's not, and the reason it's a ball is because you got pressure all the way around that ball, pressing in on it, that forms a ball. And there you go. And so you have this boiling ball. Hello. Okay. Now, if you notice on my thumbnail, and as I'll show later, the Pacific Ocean vortex, its 45-degree perimeter. Oh yeah. Imagine that. Follows right top dead center on top of, oh what? Oh my gosh. The San Andreas Fault. Imagine that. That makes sense. So the San Andreas Fault isn't going to fall off into the ocean going westward. It's going to separate from North America, just like it already has in the Gulf. Uh-oh. My computer, okay, there we go. My computer blacked out on the screen. It got tired of waiting on me. Okay. So basically the Gulf of California, right? The Gulf of California is where the San Andreas Fault is already separated. Okay, so that it's going to continue to do that. You're going to continue to see the Gulf of California increase all the way up until it's, well, gone right through San Francisco. Not all the way up to the, San Juan and all that, but it will be going up to San Francisco, guaranteed. And then go back out into the ocean. And then basically that whole landmass is going to become separated from North America and start migrating north and northwest along the northern arc of the 45-degree tangent of the Pacific Ocean vortex. Hello. Okay, now we got that one established. All right. Yeah, pretty much settles it. All right, now so I'm looking at my watch here. Oh, you know what? I gotta go. I was going to go ahead and start talking about some of the other things. I write better than I talk. And I was going to go ahead and read, the first two paragraphs of the book that I was writing, but I ran out of time, so I can't finish writing the book. Not if I want to meet the Library of Congress's 1 year mark for copyright registration stuff. And I've copyright registered a whole bunch of my terms. So, I don't care if people use them. Just can't say you made it up. That's all. So, there we go. Well, anyway, I'm going to have to let you guys go. I'll get back to you and talk a little bit more about the other things, like the other type of universe, type 2, the one that's probably responsible for how we became into existence in our universe. All right, folks, have a nice day then.